Good morning, everyone. Today I will be presenting on the project Enhanced Piezoelectric Response in Poly L-lactic acid via reduced graphene oxide incorporation. So, before moving on to the project details, some properties of the some. Let's understand piezoelectricity. Piezoelectricity literally means pressure electricity. When mechanical forces applied on the material, polarization occurs across the material and you get a measurable voltage, output voltage. And when force is applied, positive charges move to one side, negative charges move to another side, and when you connect this, you get an electrical voltage. So these materials are seen everywhere around us. The gas or barbecue lighters, they light up because of this effect. Quartz watches, and even in our body, our bones are piezoelectric. Collagen is piezoelectric. So not every material is piezoelectric. A few prerequisites for it are it should have a non-centrosymmetric structure. The crystal lattice must contain some polar bonds, and the material should have a high dielectric constant. Some common piezoelectric materials would be polyvinylidene fluoride, poly L-lactic acid, lead zirconate titanate, of course quartz, and collagen and bones. Those are natural piezoelectric materials. So now let's understand a few properties of polylactic acid, referred to as PLLA. Then move on to its piezoelectricity. Its monomer is L-lactic acid. It has four identified crystal phases: alpha, delta, beta, and gamma. Its monomer is this. And to understand piezoelectricity in it, I've taken a small polymer chain. I've highlighted the carbonyl dipoles. So these are the reasons we observe piezoelectricity in PLLA. This is its alpha phase. It's all aligned randomly, so there's no net piezoelectric output. But if we find a way to align these in a preferential orientation, then we can get a piezoelectric output. So to improve these, we have two main methods, that is by adding nucleating agents and electrospinning, or a hybrid of both. By electrospinning, so this is the setup for electrospinning. The polymer solution is kept in a syringe and that is pumped out under the influence of a high electrical field. That electrical field interacts with the polymer and it orients the carbonyl dipoles in a uniaxial alignment, and hence you get electrospun fibers. And you can use nucleating agents to induce beta phase. Beta phase is the phase where carbonyl dipoles are aligned in a preferential manner, and hence you'll get a net piezoelectric output there too. We've chosen the method of using nucleating agents. That is, we've added nano reduced graphene oxide into the polymers uh, matrix. So we've used chemical reduction to obtain reduced graphene oxide. We've used hydrazine hydrate to reduce graphene oxide to reduce graphene oxide. So firstly, graphene oxide was suspended in type 1 water, sonicated for 1 hour. Then the pH was maintained at 11. Hydrazine hydrate was added. It was kept on the hot plate for 1 hour at 90 degrees Celsius. We've characterized it through FESM, that is field emission scanning electron microscopy. Here we can see an agglomerated particle of reduced graphene oxide with a wrinkled sheet-like morphology. Now let's see how we've prepared PLLA RGO composites. We've used solvent casting, and the solvent we've chosen is dichloromethane. Firstly, PLLA pellets were dissolved in dichloromethane, kept under magnetic stirring for 18 to 24 hours. Then separately, we've added nanofiller and ethanol. We've sonicated this too. And finally, these two solutions were mixed and then cast onto a Petri plate. For PLLA RGO composites, we have also characterized it using FESM. So here you can see an RGO particle embedded in the polymers matrix and the texture of the films. We've also characterized it using FTIR, Fourier transform infrared spectroscopy, and we've done X-ray diffraction studies. So if you see the FTIR spectra, there's not much difference. So this is PLLA control. These are the varying concentrations. But if you zoom onto the spectra in this region, we can see a small peak at 910 centimeter inverse, and this is reported to be the characteristic beta phase peak for PLLA. That is equal to preferential alignment of carbonyl dipoles. And X-ray diffraction there's a lot of difference in the compared to the control and to the varying concentrations, but these are amorphous peaks attributed to reduced graphene oxide, but there are small peaks here which are attributed to beta phase PLLA, and beta phase PLLA means preferential alignment of carbonyl dipoles. So we can hypothesize that better piezoelectric output will be obtained with these PLLA RGO composites compared to control PLLA. So let's to test that hypothesis, we've used this method. We've made piezoelectric devices by sandwiching the active material between two copper electrodes and securing it with Kapton tape. This was the setup that we've used for testing the device. This is the picoscope which measures the output voltage. The piezoelectric device was placed here, and we've used biomechanical hand tapping. So to see how much force we are applying and to control that, we've used the dynamical force sensor, and force was applied at 0.5 newtons and 1 newton. And this is the output voltage that we've measured. Now let's look at the results that we've obtained from this method of testing. If you see the graph, this is PLLA and these are varying concentrations. So PLLA control has around zero point 0.6 volts of output at 1 newton biomechanical hand tapping, and PLLA 0.75, that is RGO 0.75, that is 0.75 nanofiller loading, you get 2.2 volts. So that is a 2.6 volts, sorry, and that is a 72.2% improvement already. So we have successfully improved piezoelectric response in PLLA using reduced graphene oxide. So we can say that reduced graphene oxide has oriented the carbonyl dipoles in the polymer's backbone chain, which is confirmed by the FTIR and XRD spectra. And the optimal, and again, if we see here, there's no observable pattern here. So the optimal concentration is 0.75 weight nanofiller loading, and hence addition of nanofiller RGO has improved piezoelectricity in PLLA. I would like to thank everyone who's been a great support throughout this project, and thank you all.